Hey guys, Mr. Betts here. I want to go through an example where we have a definite integral, and I actually want to go all the way through the process of evaluating the limit that we get that's equivalent to this definite integral so we can actually find the area. I want to mention a couple of things. First of all, this is a process I'm not going to expect you to be able to do on your own, so you won't see something like this on an assessment. It's also a process that's going to be very limited, and it works because we have a polynomial, and specifically a polynomial that's only second degree. So we can use some identities that are really not calculus things, but these formulas down here we're going to be able to use. So before I get into this, I just want to mention what these mean right here. So just taking this one for example, what that means is if we want to say, let's say n is 10, then what this is saying is what is 1 plus 2 plus 3 plus all the way up to 10. And what the formula tells us is I can plug 10 in for n here, and that's going to be 10 times 11 divided by 2, which is 55. And if you actually add up the numbers 1 through 10, you can confirm that that works. That works for any n value, no matter what n is, as long as it's a positive integer. I shouldn't say any, no matter what it is. And so we can do the same thing with these other ones. So for example, if we're going to add 3 plus 3 plus 3 plus, let's say 10 times, so we plug 10 in for n, we plug 3 in for c, and we get 30. Over here, if we do 1 plus 4 plus 9 plus 16 and so on up to, say, 100, plugging 10 in for n there, that sum is going to be 10 times 11 times 21 divided by 6, which is what, 5 times 11 times 7, 35 times 11, 385. So a quick formula that gives us that. Okay, so let's jump into the definite integral now. So the first thing I'm going to do is I'm going to rewrite this as a limit, and I'm going to use RRAM. In order to do this, I need to know what delta x is. So delta x is going to be b minus a over n, which is 2 over n. So it's going to be 2 over n times the sum I equals 1 to n of f of a plus I delta x. So f of a plus I delta x. So a plus I delta x is going to be 1 plus 2I over n. So f of this, plugging this in for x, we're going to get 1 plus 2I over n quantity squared plus 2 times 1 plus 2I over n. Okay, now I'm going to do some simplifying. So this right here, we can just simplify algebraically. I'm going to do a little bit of that work off to the side just so I can save space in here for my work. So this part right here, if we square that, is going to be 1 plus, looks like we're going to have 4I over n plus 4I squared over n squared. And then the 2 times 1 plus 2I over n is going to be 2 plus 4I over n. So we're going to add those together now. So we got 2 over n times the sum from I equals 1 to n of, I'm going to do the I squared term first. So I'm just adding these together. So we have 4I squared over n. And then we're going to have 4I over n plus 4I over n is plus 8I over n. And then we have plus 2 plus 1 is plus 3. Okay, next thing I'm going to do is I am going to separate this into 3 separate sums. So if you think about what we've got here, each one of these terms is going to give us a term in the sum. So if we were to write out this sum here, I'm going to call this a sub I, b sub I, and c sub I. We're going to have an a sub 1 plus b sub 1 plus c sub 1 That's going to be when I equals 1, and then A2, B2, C2, and then A3, and so on, right? Well, what I'm going to do is I'm going to write them as separate sums. So I'm going to put the A's in one sum, I'm going to put the B's in another sum, I'm going to put the C's in another sum. I'm just rewriting this using a property of sums. And it's not going to make things look simpler, but it is progressing toward our final answer. So we're going to have the sum from I equals 1 to n of 4i squared over n plus the sum from I equals 1 to n of 8i over n plus the sum I equals 1 to n of 3. Okay, the next thing I'm going to do for each one of these sums is I am going to factor out anything that doesn't depend on I. So when we're writing out this sum, I'm just going to take the first one as an example. We're going to have 4 over n times 1 squared plus 4 over n times 2 squared plus 4 over n times 3 squared, and so on. And so that 4 over n is appearing in each term. So I'm going to factor that out. So that's going to go outside of my sum. And so we get limit as n approaches infinity of 2 over n. All right, so we've got 4 over n times the sum from I equals 1 to n of I squared. Now, before I go any further, I want to point out why I'm doing this. This right here, we have a formula for right here. So my next step now is going to be to replace this with that. Okay, moving on. The next one, we're going to factor out that 8 over n. So we're going to have 8 over n. Uh-oh, I made a mistake. This should be an n squared here because it was an n squared up here. And that's an n squared there. Okay. Okay, so 8 over n times the sum from I equals 1 to n of I plus, and then the last one I'm going to keep the same because I can use this formula there where C is just 3. So sum from I equals 1 to n of 3. Okay, now I'm going to distribute this 2 over n here. So I'm going to multiply that by each of the coefficients. So we get limit as n approaches infinity of, so it's going to be 8 over n cubed, sum from I equals 1 to n of I squared. And then we're going to have 16 over n squared, sum from I equals 1 to n of I. And then we're going to have 2 over n, sum from I equals 1 to n of 3. Sorry that I'm squeezing it together here, but I promise we're getting kind of close. I do want to point out that this isn't really looking any simpler, but we are working toward a point where we can start simplifying. So I'm going to keep the limit out front here. Limit as n approaches infinity. And now what I'm going to do is I'm going to replace each of these with the equivalent expression from our formulas down here. So we're going to have the 8 over n cubed times the I squared formula we're going to replace with this. So n times n plus 1 times 2n plus 1 over 6. Okay, so that's this one. Then we're going to have plus 16 over n squared. And then times n plus 1 over 2. And then the last one, we're going to have 2 over n times 3n. Okay, now this looks even more complicated than the last step. However, we are at a point where we can actually evaluate the limit. That's exciting, right? So if we look at each term individually, think about what happens when n gets really big. What we have here is a polynomial divided by a polynomial. And if you remember, when we have a polynomial divided by a polynomial and n is approaching infinity, we can evaluate that by looking at the largest degree term at what's going to dominate the numerator and denominator. So in this one right here, the largest degree is going to be what we get when we multiply n times 2n times 8. And so we are going to have other terms, but the important thing is the n cubed term is going to be 16n cubed, and on the bottom we're going to have a 6n cubed. So this expression is going to be dominated by 16n cubed on top and 6n cubed on the bottom, so we get 16 over 6. In the second one, we're going to have 16 times n is 16n squared. And on the bottom, we're going to have 2n squared. So we're going to have plus 8. And then the last one, this actually doesn't even depend on n because the n's cancel and we get plus 6. So last thing I'm going to do here is just some simplifying. We have 8/3 as our first one, plus 42/3 is going to be 50/3. And that's our answer. So what that tells me then is if we go over to our graph here, this area right here is, using this limit, exactly 50/3 or 16 2/3. So we can evaluate this exactly and say that that area is 16 2/3. I want to mention again, this is not a process I expect you to do on your own. It is a process that's very limited because we had a polynomial here. If the degree gets too big, basically beyond a third degree polynomial, or if it's not a polynomial, it's more like a sine function or an e to the x function or a natural log function, this process will not work. However, it does work, and this is the first time now we are actually able to solve the area problem for a function that doesn't give us just a rectangle or a trapezoid or a circle or some basic geometric shape.